Good morning students, welcome to YouTube channel Next is You. In the last class we studied about boundary value problems. Today we discuss some numerical based on boundary value problems. So first problem is two infinite parallel conducting plates are separated by 5 centimeters. The upper plate is maintained at 100 volt and the lower plate at 0 volt. We have to find the potential distribution Vx, the potential at x is equal to 2 centimeter and the electric field between the plates. Since the space between the plates is charge free, so here we have a Laplace equation del square V is equal to 0. For one dimensional variation, we have d square v upon dx square is equal to 0. When we take an integration, then we get a potential v is equal to c1x plus c2. Now using a boundary condition. First condition is at x is equal to 0, we have potential 100 volt. Since from putting this value in this general solution, we get C2 is equal to 100 volt. At x is equal to 5 centimeter, potential is 0. So when we use this value in general solution, then we get C1 is equal to minus 20. And when we put these C1 and C2 in this general solution, we get potential that is 100 minus 20x, where x is in centimeter. Now we have to calculate potential at x is equal to 2 centimeter. We just put the value of x is equal to 2 centimeter in this solution. We get V is equal to 100 minus 20 into 2, which is equal to 60 volt. Now in order to calculate the electric field, we have to take a derivative of this potential with respect to x. So we get E is equal to minus dV upon dx, and here E is equal to minus into minus 20 and we get 20 volt per centimeter. Next question is a one dimension region satisfies the Laplace equation. Given the boundary condition for this Laplace equation is V0 is equal to 40 volt, means at x is equal to 0 we have a potential 40 volt, at x is equal to 10 centimeter we have a potential 140 volt. Find the potential at 6 centimeter. We have to calculate the value of potential for Laplace equation at 6 centimeter. We know the general solution for the Laplace equation, which is equal to C1x plus C2. When we using a first boundary condition, that is V0 is equal to 40, means at x is equal to 0 we have a potential 40. When we use this value in the general solution, we get C2 is equal to 40. And when use the second boundary condition at x is equal to 10 centimeter, we have a potential 140 volt. Then we get the value of C1, which is equal to 10. When we use these two values C1 and C2 in this general solution, we get the potential that is V is equal to 10x plus 40. Now we have to calculate the value of potential at x is equal to 6 centimeter. While using this x is equal to 6 centimeter, we get potential is equal to 100 volt. Now the next question is the electric potential in charge free region. So charge free region for Laplace equation. We have a potential Vx is equal to 60 minus 15x, where x is in meters. Now first of all we have to calculate electric field. So electric field is nothing but a negative sign derivative of potential. And second is potential difference between x is equal to 1 meter and x is equal to 3 meter. Here we have to calculate the potential difference between x is equal to 1 meter and x is equal to 3 meter. Now the electric field is E is equal to minus dV by dx. Now we have to take a derivative of this potential with respect to x. Then we get dV by dx is equal to negative sign of 15, and when we put this dV by dx in electric field, then we get E is equal to 15 volt per meter. Now we have to calculate the potential difference at x is equal to 1 and at x is equal to 3. So when we put the value of x is equal to 1 in our given potential, we get 45 volt, and when we use the value of x is equal to 3 in our given potential, then we get the value 15 volt. Now we just have to take a difference of these two values, so potential difference is nothing but 45 minus 15, which is equal to 30 volt, and we get the potential difference is equal to 30 volt. Our next question is the potential inside the region. Now we have a potential inside the region which is V is equal to 80 minus 4x. Find the boundary potential. We have to find the potential at boundaries where x is equal to 0 and for x is equal to 20 meter. Now solution, we have x is equal to 0. So if we put x is equal to 0 in given potential, we get V is equal to 80 volt, and at x is equal to 20 meter we get the potential is equal to 0 volt. Hence the boundary conditions are at x is equal to 0 potential is 80 volt, at x is equal to 20 the potential is 0 volt. Next question is determine whether the following function satisfy Laplace equation. We have a function v is equal to x square minus y square. Now we have to satisfy this potential as a Laplace equation. We know that the Laplace equation is del square v is equal to 0. Now in the Laplace equation for two dimension we can write curl square v upon curl x square plus curl square v upon curl y square is equal to 0. Now we have to take a second derivative of potential with respect to x, and also we have to calculate the second derivative of potential with respect to y. Now the second derivative for the first derivative of potential with respect to x is 2x, and the second derivative of potential with respect to x is 2. Similarly, we can calculate the second derivative of potential with respect to y, which is minus 2. When we use these two second derivatives with respect to x and y in this equation, Laplace equation, then we see that 2 plus minus 2 is equal to 0. So this equation satisfy the Laplace equation, means this potential satisfy the Laplace equation. Next we have the electric potential is V is equal to 3x plus 5y minus 2z. Now in this potential we have this potential is a three dimension, that the value of x, y and z. Now the second derivative with respect to x, for this potential we have curl square v upon curl x square is equal to 0, and the second derivative is curl square v upon curl y square is equal to 0, and the second derivative with respect to z is again curl square v upon curl z square is equal to 0. When we put all these value or take addition of these value, then we get a Laplace operator, that is del square v is equal to 0, and we have a Laplace equation del square v is equal to 0 which satisfy this potential v is equal to 3x plus 5y minus 2z. Now the potential between two conducting plates separated by 4 centimeter is given by. Now we have a potential where the two conducting plates are separated with a 4 centimeter of a distance. Now v is equal to 100 into 1 minus x upon 4. First we have to calculate the potential at x is equal to 1. We just put this x is equal to 1 value in this potential and we can calculate the potential at x is equal to 1. So the potential we get is v is equal to 75 volt when we put x is equal to 1 in this potential. Now in order to calculate the electric field, we have to take a derivative of this potential with respect to x. So E is equal to minus dV by dx, and after differentiating the potential with respect to x, we get minus 100 upon 4 which is equal to minus 25. So when we use this dV by dx is equal to minus 25 in this value, in this equation, then we get E is equal to 25 volt per centimeter, because negative sign here is cancel out. A one dimension region satisfies the Laplace equation. The boundary conditions are, so we have a boundary condition V0 is equal to 0 and V8 is equal to 40 volt. Now we have to calculate the electric field. Same procedure has been followed, that is general solution for Laplace equation is V is equal to C1x plus C2. For x is equal to 0 we have a potential 0. For x is equal to 8 we have a potential 40 volt. Now using this simple calculation by putting all these value, we get our potential which is equal to 5x, and when we take a derivative of this potential with respect to x, then we get a electric field. So this is all about the numericals that related to boundary value problem. In the next session we will start with the Bayes-Savage law. Thank you and have a nice day.